So welcome everybody. And today we keep on doing this introduction to deep learning, and we're gonna talk today on convolutional neural nets. So basically the idea is to introduce the key concepts to this type of networks. They have a specific architecture and the sort of materials if you want to cover. If you want a super quick introduction, CASI 18 is a good reference. If you want a kind of technical, a little bit mathematical introduction, the chapter 9 of Goodfellow. And if you want a more descriptive computational, the Cholet chapter 5, it's a very good source actually. And as usual, I shall do a little bit of conceptual introduction, but then Nacho Villanueva, if he comes and finds the room today, he will come and he will talk on a project that they are doing, a very interesting project that they are doing on forecasting eolic energy production. Actually, it's a bit more on renewable energy production forecasting. There's also two very sort of, if you want, I don't know, if you only have like 15 minutes to understand what's going on, this video explains quite nicely in 15 minutes what's going on, and it has some kind of nice images. And if you have only like let's say 1 hour to understand various models, etc., this is a very quick and easy to follow introduction. And as we always comment, probably there is more to learn through the labs that are available. And let me just describe what we are doing in the labs. We work with a set which is quite famous in this area, which is MNIST, which is basically numbers, handwritten numbers by Lecan and his colleagues from, I don't know, almost 30 years ago. So that's a very well-known data set. And then what we do are all these blocks. So first we do a logistic regression to forecast or to predict what numbers are written. It's presented as actually a logistic regression presented as a neural network model in the Keras notation. And then we improve it by properly rescaling the data. So that's quite important. That's a sort of caution note. In general, as we have expressed through various examples, that we quite frequently need to pre-process somehow the data to get better results. Then we go through one of the models that we saw last week, which is a fully connected network. With two ways to regularize. One is through L2, that's rich regression. I mean, it was what we call rich regression. In this domain, remember that we call it weight decay, and then with dropout. Then we illustrate a couple of things which are more of model keeping, which is how to store the model that we find, and then how to reload it to make forecasts. That would be quite important. Then we, as a comparison, remember that we had this discussion of no free lunches. We compare it with random forests. And then finally we do a convolutional neural network with this same data. And as we mentioned the other day, we normally do several rounds, what we call epochs. So that's kind of interesting in the sense that we are, I mean, like my computer, which is my very simple computer, we can only do 2 epochs, and that's typically very low in this domain. So this is, this is like, this lesson or this kind of models mark somehow a frontier. So we've been doing, let's say, computationally easy model so far. But now we need to go to, I mean, with these kind of models, this marks the frontier that we need to go to a high performance computing installations. So that's why we in the lab we have a sort of version, an R version for a PC, which runs with just two epochs. But then we have another version based on Google Colab, which is a platform which is free of use, and you can do it. But remember that that's let's say publicity for the people at CSIC. We have a number of platforms available. These two are available for the whole National Research Council. So there is this Drago, which is located somewhere in Madrid, right? Which is available. This is starting to run right now. But this one is Artemisa, which is somewhere in Valencia, and this is quite powerful, and they're all very willing to support high performance computing. And again, I mean, typically, I mean, of the 3 or 4 institutes that I know better typically they have installations, our own or your own installations. In our case, at the mathematics, we have Lovelace, and that's available also for use. And we have smaller machines. So, I mean, basically, the basic message is we cannot anymore do computations in our machine. Yeah, pardon. That's it. So we need to do other machines. Okay, so that's actually we said that we're going to do a NIST in the lab, right? These are the type of images that we use. So this is sort of a nice version when the image is rasterized, right? So that would be like a 1, and we need to recognize this as a 1, right? But the type of data, when you sort of show them in a sort of colored version, they look more like this. So this is actually a matrix 28 by 28, and the color indicates an intensity. So the darker would mean, I mean, the numbers go from 0 to 55. So these will be zeros, right? And some of these, the darker, are close to 255. So this is actually a matrix of numbers. So this nice thing is actually a matrix of numbers that we need to handle, and that's how we handle them. Okay, so first a bit of motivation. I'm doing this in English because Sonali is. I will introduce it to you, I promise. So. If you remember last week, we said we talked about fully connected neural nets, and we said we mentioned 2 or 3, and there's many more results. We say that they can approximate any function, right? But we mentioned as well that training can be super slow and may require lots of data. And the thing is that people over the years have discovered or studied special structures or special architectures that work much better in some domains. And today we'll see one of these examples, which are convolutional neural nets. In origin, they come from the vision domain, right? I mean, we saw one example which was recognizing numbers. But they can be used for several purposes. For example, we will focus on 2D, so on 2D ComNets, but I think yours are 3D, right?
I'm using 2D and 3D.
Right. So Nacho will talk about 2D and 3D. You can use it 1D convolutional nets for time series forecasting. But actually, I mean, so let's say old types of models for time series, there were better options, and now there's better competitors within the neural net domain, right? I mean, the sort of origin and sort of best place for this are 2D convolutional nets, right? ComNets for image recognition and et al. And this et al is super important. For example, this is essential for, I mean, this technology is essential for automated driving systems, which is, I mean, we have a little bus, autonomous bus running in the campus, but this is a technology which will change the world as we know it. So automatic driving systems in part have been made possible because of this type of technology. Here I said, but there are better competitors. One interesting, I mean, this is an interesting time for this because the kind of models that we'll see next, well, after Eastern, which are recurrent networks, etc., are starting to be used. Transformers are starting to be used for vision, and there's already some claims that they perform better. So maybe whoever talks about this next year will need to talk about transformers for vision rather than this one. And finally, 3D ComNets are useful for video processing et al. And again, et al means ADS, which is quite important. Okay, so a bit of history. There's one thing which is interesting of ComNets is that these models are actually related to some neurological process. So what we said the other day that all this had a very good branding, or from a point of marketing perspective. Whoever invented the term made a marketing hit, right? He sold the things better than mathematicians or statisticians usually do, right? So he found a very sexy name, etc. But actually, he said that there were some connections with neurons, etc. But it's actually very, 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 very weak. But in this case, it's actually it has a very deep connection with the neurological aspects, and actually is very much related to how cats see. So that's a word of Hubel and Wiesel. They got the Nobel Prize in medicine and physiology, and because of the work that they did. So based on that, this Fukushima introduced an architect which was called neocognitron, very, very close to Hubel and Wiesel's development, but without a training algorithm. And LeCun actually made the connection between neocognitron and backpropagation that we saw the other day, and it led. They developed the first convolutional nets as we know them today, and they use it to handle the NIST data set that I mentioned before. And the sort of network that they introduced was LeNet or LeNet 5, and it was, I mean, they actually made a nice business from that. And then basically everything was kind of frozen until the 10s, in which there was this network AlexNet, which was used to recognize, I mean, it was used to handle a very big database with 1.5 million images and recognize 1,000 types of objects, persons, cats, plants, whatever. And then the sort of important milestone were when these two networks won this competition, ImageNet, and this actually was the beginning of the explosion of interest, first on convolution nets, and then on neural nets. So that's a little bit of the history.
David. So, for instance, in this Alex net, you would have a number of features for the first.
Yeah. Yeah, typically, well, it will be an image like the one that I showed you before. It was a 28 by 28. These are more. I think it's something like 350 times 350. So it's an image. It's my face, for example. But my face is a matrix of, I don't know. Depends on the resolution that you are able to, 28 by 28 or whatever. So my face is a matrix of numbers. So I don't know, this
I see your face.
yeah. So this is a darker part, and this will have a 250 something. This white background will be a 0, right? So it's a matrix of. So the features, what you introduce is a matrix of the dimensions and a matrix of numbers, and this is what is going to be introducing there. Okay. Yeah. So so we go back to Carlos Oscar talk like 2 weeks ago, and we mentioned this. So that's part of the sort of interesting part. So we had objects to be classified before, and as Oscar showed, he spent lots of time on trying to extract features manually. So he made all these alterations of the Fourier transformations, whatever, and then he was getting features connected probably with what Jesus was asking, and then he was using a trainable classifier. In his case, it was a SVM, right? So now what is that the trainables, there's a trainable feature extractor, so we don't spend a lot of time, or a lot of imagination trying to get features, but our net extracts the feature, and then there's a trainable classifier, and typically these are integrated as well. Right? So that's the change of parameter that we've mentioned and that we've illustrated, right? So that's the typical thing. I mean, so that's how we start, and we want to recognize that this is a car, right? Okay, and basically a convolutional neural network, it has a pile of, it has a hierarchical procedure to extract features. So in the beginning, there's like low-level features, right? So in the beginning, so we get things which are quite close to, like, I don't know, borders or yeah, okay. Then we go to more. We go up in the hierarchy, as we shall see in a minute, and get like more abstract things, right? Like this. And then these are the kind of abstract features that are introduced or input in the classifier, a standard classifier, and this should tell us that this is a car, for example, or a yellow car or whatever, right? So that's a basic idea. Yeah.
Those are the features, or not specific for classifying cars, right? Those are the features extracted for classifying images.
Yeah.
And then, so it's not this.
Yeah. So yeah. Basically, it will identify like borders of things or details, or I mean, it depends on the problem. It will depend on the problem. If you just train to differentiate between cats and dogs, so it will identify, right? But in a image, I mean, this competition AlexNet, for example, in ImageNet, there's 1,000 different types of objects. So we need to differentiate.
This is not a 5 by 5, it's a 5 by 6. When does it decide how many?
No. This is just we'll go to this. This is just sort of didactical device. But this is a very important point that you've just made. So basically, the idea is that I mean, in essence, in a fully connected, each of these would be like one of the hidden, let's say, of the first layer, a hidden node, and the hidden node needs to cover the whole image. So it needs to learn globally, what is a car, right? And that gets very complicated. Lots of parameters, etc. With this, they just focus we'll make it a bit more precise in a minute. On let's say local. So it will learn about I don't know, years, and it will try to learn what's a nose, etc., or what is the border of an image, and therefore it gets more efficient. So, three essential concepts or important concepts, which are convolution. What is it's called convolutional, so convolution it's relevant. The second thing is that we mentioned the other day is the change from sigmoidal to ReLU activations, and then an operation which is called match pool or pooling. In general, is pooling. In particular, the most popular is match pool. Though some of the most recent architectures no longer use match pooling. These are we mentioned this, but it has been used for sound analysis as well, but also for pharma discovery, drug discovery, etc. And so that's quite important. And that would be like a first example. So you can see there, you can see in this architecture. So there's convolutions, there's ReLU here, match pool, etc. So it's a combination to do, and then some classifier. So we will understand these blocks, but the three concepts are convolution, ReLU, and match pool. Okay. So the three concepts. First one is convolution, which is mathematical concept which is used in many, like for example in statistics we use it. We use something which is exponential smoothing for forecasting, and that's convolution. And we have very distinguished mathematicians which will, but basically that's the general expression in the case of discrete time, right? You can do it, but it's used in signal processing a lot, etc. Right, so that's it's just a linear operator, right? And in deep learning, in convolution nets, basically there is an input which is I, which is an image, right? It's a matrix. Basically, it's a matrix, right? It could be multidimensional. It could be, for example, a color image, and therefore it has three channels: red, green, and blue. So it's basically three matrices, right? Three two-dimensional matrices. What I was saying, yeah. So convolution means multiplying by another matrix, and basically what it amounts is to a matrix which is circulating over the input to produce some output. So basically, in a scheme is suppose that this is the image, which is a matrix, right? And we use a kernel, right? These are the weights of the kernel, and these are the weights that we need to learn, right? Okay. So this is a circulating matrix. So this multiplies. Basically, this operates over with this, and producing this operation. Then it moves a little bit to this one and summarizes everything or processes all this information in this, and then it moves, and then it moves here, etc. So multiplying this input with this kernel leads to this output, right? And well, as I said, the idea is that we shall need to learn these weights for the purpose of recognizing images, or for whatever purpose we consider. Okay. Now, the sort of three features which are quite important are, let's see, which ones are they? The first one is sparse interactions, less dense interactions, right? So I'm putting here. I mean, one of the things is that we shall need. I mean, we use less weights, right? And this means we need to store less information, and we need fewer operations, right? Okay, so this will be the case of a fully connected layer. So these are the inputs, and this is the so these are fully connected, and therefore, I mean, you can see that this input affects all of these affects all the intermediate or hidden nodes, right? And similarly, each hidden node is affected by all the inputs, right? In this case, we have a less sparse interactions, right? And actually, this input affects just these hidden nodes, and similarly, this hidden node is just affected by these three outputs. Actually, but actually, there could be, I mean, in a sort of more abstract or higher hierarchy, I mean, there could be interactions between. I mean, we recover all the possible interactions at a higher level. So, for example, if I pile a couple of convolutional layers, then I mean, you can see that this one, for example, which is affected by these three, but in the long term originally is affected by the whole thing. So, but this makes it. So this is the first sparse interactions. The second one is parameter sharing. And here is one, in this case, in this example, this fully connected, this parameter which goes through this connection is just affecting this relation, right? But in this, because there is, I mean, the filter is moving, right? It's shared in all these parts, and therefore again there's economy, etc. And it has the sort of implication of this is quite important for image processing, because low density and sharing is the responsible of being in a quite nice way, being able to detect, I mean, feature extraction in general, and in particular edge detection. For example, just by removing the pixel, I mean, remove to each pixel that of its left in this image, you get this. And in this example, with more than one filters, you get different versions of the. And that's the idea. That's okay.
Can you explain a little bit more? What do you mean by remove?
Yeah. So let's suppose that. I mean, this image is actually something like this. Right. So if you well, like this one, one which is in the border. So it's this one, right? If you remove this from this one, right? This will be I don't know 200 and I mean it will have some value. If you remove it, then you recover and you represent it like this, you recover this kind of image, right? So remember that this image is actually a matrix of numbers. So this number less this number will lead you to this kind of thing, right? I mean, black minus black will be somewhere like there, but this one with this one, this difference will give this difference.
So you're subtracting.
Yeah.
Yeah, and if you get below 0, you just put a 0 there.
Yep.
Okay.
Right. And the other important thing is of these nets is that they preserve. I mean, these differences, etc. These operations, these linear operations, are preserved with translations, which is quite important for visual stuff. Okay. So that's the basic. These are the basic concept of convolution. Now there's 2 or 3 things that are important. 2 or 3 concepts that define a convolution. 2 or 3 additional parameters we define a convolution. The first one is what is called the convolution stride. And basically, in the example that I mentioned before, we were moving here, and then we were moving one pixel to the, and then and when we finish, we move one down, etc., etc. That's a stride 1, right? That is called a stride 1, right? But it doesn't. I mean, you could do a stride 2, and this means that with this, this is the with a 3x3 kernel. So you, rather than moving to the next one, we move it 2 pixels, and then 2 more pixels, and then you are done. And then once you are done, you don't move to this one, but 2 pixels down, etc., etc. So that's the stride. Stride 1, stride 2, stride 3. So bigger stride means less cost, and of course less detail, but sometimes that's better, or that's sufficient. It's sufficient detail with much less cost. So the stride is quite important.
So there are 2 things. There is stride is one variable, and then the
that's the kernel, the choice of the kernel, which connects with what you asked before. So normally, I mean, you pick a small size kernels, like 5 by 5 or 3 by 3, or okay, that's the big function.
What gets affected? The kernel size in combination with the stride. What is best? Like, is it a bigger kernel size with small strides better, or
that's a matter of the computations that, but the idea is smaller kernels gets more detail, right? That tends to give you more detail. Smaller stride tends to give you more detail, but more computations, right?
But if I have to choose one where I can be less computationally expensive,
we'll go to this one. I mean, the basic image is that there's people who have worked, who have worked with computers for many weeks, and there's a number of architectures which are already available in many, and we'll see the trick basically, and we'll discuss it. But that's a very important. I mean, that's a typical. How do I go with this? But we'll answer to this question in like 10 minutes, right? So stride is important. The other thing is zero padding. Padding, right? So if suppose that this is your image, right? I mean, represented in such a way, right? So I mean, that would be pixel number 1, etc. Right? If you apply a convolution in this case, right? As in this case, so what you can see is that there is a reduction, right? Right? That's 3, 4, that's 6, right? So there's a reduction, etc., and there's a point in which you cannot add more convolutional layers, right? so it gets shrinked, right? So the way to mitigate, I mean, if you want, so let's say you cannot get too abstract, right? So if you want to get more abstract, the way to do is to pad this with zeros, right? And then you don't get shrinked, and you could add more levels of abstraction. So that's basically the idea of zero padding, right? For example, you have here an example. That was the image originally, right? But we have padded it implicitly with zeros, right? And then we don't lose that much. I mean, this doesn't get that small, and we can, right? So these are the parameters that we use the stride in connection with Sonali just mentioned. The kernel size, usually square, and typical choices are 3, right? Then we need to consider the number of kernels. So let's say, I mean, we're gonna consider like 32 kernels. So okay, so each one will be a matrix, right? We need to learn the weights of that matrix, right? That's what we need to learn, right? And let's say each of these kernels will take care of some aspect. So this kernel will be the kernel who takes care of, I don't know, the ears, and this kernel. Okay, we'll see an example again. And then the final decision to be made, and when we design this, is whether we pad or not, and the type of padding that we. We'll see an example in a minute. Next thing is, rather than we use ReLUs, rectified linear unit, and some other variations, which is this one, right? So it's more computationally more efficient than the other. So it alleviates the vanishing gradient problem that we mentioned, and the derivative is simple, right? Okay. So this is the except here, right? But this happens with very small probability, and if we find out this, we can either choose the derivative is 1 or 0. It depends on what you want, right? The third, we said convolutions. What do we say? Yeah, ReLUs and max pool. That's the third ingredient, or the third new thing, if you want. And max pooling is basically a way of down sampling, right? So basically, at some point, I mean, to go more abstract, well, you're getting, but you somehow to become more abstract, you want to somehow summarize, let's say, what is going on in this. We need to summarize in this 4. You summarize it in just one thing, right? So, and one thing is, remember that these are numbers. This is an image, but it's reflected in numbers. So one way to summarize this is through the maximum of these numbers. So like, for example, this is a 1156. So you summarize this. If you decide to use max pooling, you summarize it with a 6, and this you summarize it by 8, etc., right? So you could imagine that. I mean, assuming that this is the likelihood of this pixel, okay, so you are summarizing this by the maximum likelihood. You may make this kind of conceptual jump if you want, right? And so that's a way to abstract. And for example, this image that we had before, and we make a max pool of 3 times 3. So we are basically summarizing. So we get something which is a little bit more abstract, right? There's other people who use average pooling, etc., but that's the favorite. And as I said, some recent architectures don't use pooling. Sorry. So these are the three elements. The typical architectures have the typical structure is there's an input to a layer. This is the convolutional layer, and basically it has a convolutional phase, which is a bunch of affine transformations. Then there is a detection phase, which is basically passing through the nonlinearity, the ReLU, and then there is the pooling phase, which is abstracting, and that's the output. And then we pilot another layer comes. So that would be in a picture. So that's that was our image, which is a matrix, right? We have padded it, right? And then we pass a filter like this is one filter which is passing like this, and this produces this one and this one. Okay, so there is this transformation, and we use a bunch of filters. Okay, right? Then we max and plus red. Then we max pool and then get a little bit more abstract. Then we pass filters again, etc., etc., etc. So that would be the basic architecture. This is in a sort of different way. So you put these are the entries, and then there's convolution, and this would be the classifier, and it will give us the classification. And that's in a sort of actual example. So this is the car. We want to classify this as a car, right? Imagine that I have a car, an automated car, which is getting images, and it needs to classify a car, right? So basically, it goes through convolutions. Here it's a convolution ReLU, then pooling, etc. So basically, it starts with several features, applying several features. Which get various, it gets not so abstract here. These are borders or identifying various aspects of interest. Then there's the activation. Another, you can see that in the next convolution, it's a little bit more abstract, but you can still recognize something, and it gets more abstract, etc. Blah blah blah. In the end, the classification is based on this, which is super abstract. Right, so you feed this to a classifier, and this will tell you. The classifier will tell you that with a certain probability this is a car, with a certain probability it's a truck, etc., etc. And the most likely object in this case is a car. So that's a car, and therefore my system makes the decisions. Which if it's a car, it will it will break or it will. Okay, so that's basically. So that's basically the spirit of the thing.
So the classifier is in a neural network that you've already trained?
No, no. The whole network is the neural network is the whole thing, right? Right. It has some a bunch of convolutional layers, which basically what they do is get features more and more abstract, and they typically these are the features. Let's say this last one. This is feeding the last layer, which is a classifier or a standard classifier, right? And this is the classifier which tells us what is this object, right? So, but the neural network is the whole architecture. It's not this. Is the model which is providing these outputs, right?
Yeah, but for these things, you're not applying gradient descent.
Yeah. Okay. This, this is using. This has already. This has like 3, 6, 9, 10 filters, so 10 matrices, 10 of these things. This has each of these has its weights, right? Right, so each of these has, these weights, right? Okay, it has its own weights, and these weights have been learned by showing, 1 million images, right? and well, we were saying this, it was doing some, and it was checking whether this was a car or not, right? And based on that, it confused the gradients, etc., right? So this is the sort of how do you use it? But I mean, to get this, there's been a learning process.
So the structure that you use is totally heuristic, like it's just by trial and error, or is there any ideas behind the number of layers that you put and the type of kernel that you use?
There's a lot of heuristic, I would say. Yeah. A lot of people who have tried, etc., and it's basically a lot of burning machines, etc. Yeah. I would say that's a sort of major issue. Let's call it rational design of architectures. That's a major issue. Which, by the way, you can solve it through Bayesian methods, but it's too complex. For shallow networks, you have nice ways to choose the architecture, but for deeps, it's very difficult. So there's lots of experience accumulated by many teams in many organizations, and yeah.
So why didn't it? So 1/3 of the image is forest. Why didn't forest come as one of the options? Why is it taking the center thing and trying to identify that?
Okay, because yeah, sure. Because connecting with Jesus' question, is when somebody trained this, it was looking for car basically in the this network was trained to distinguish between cars, trucks, airplanes, ships, and horses, right? For example, yeah.
It's not just a random image. There's a purpose to that.
Yeah. I mean, you taught in the case of ImageNet, you have taught.
What if I wanted to identify forest from the picture?
Probably if in ImageNet there were forests or trees, then you're done, right? But if not, you will need to get lots of forest images or types of. If you want to differentiate between different types of trees.
Or just
then
this,
you need
is the car driving? What is the background of the?
Oh yeah. Actually, you can. Another problem which is related is actually in automated driving systems. That's an essential problem. It's not just the car, but you need to. There's several cars. There is a car, but there's some people here, and there's a sign, a speed limit sign there. So you need to recognize several objects. Yeah. There's a multi-object recognition problem. So as an example, in the lab, so to recognize MNIST, which are 20 by 28 matrices, right? Of from 0 to 255, the intro. 0 means white, 255 means the darkest, right? Sorry. So that would be related with your question. So there's a convolutional layer with 32 filters. So there's 32 matrices. These are 3 by 3 and ReLU. There's another layer like this. Then there's max pooling, and then there's 2 sort of traditional or fully connected layers. The last one, because we need to recognize between 0 and 9, so there's 10, right? 10 units, and we use a softmax. So that's a standard or traditional classifier. And that's how it looks. I mean, you can see that this is keras for R. So you can see that the language is quite similar to, if we write it like this, so you can see, for example, there's a 2D convolutional layer with 32 filters. There are three activation is relu, and that's input parameters. So, right, and also all the things that we mentioned before. We say nothing about stride, so the default stride is 1, right? So, but we could write stride equals 2 or stride 3 or whatever. And if we say nothing, there's no padding. So in this case, there's no padding. Some standards. Then there is. This is partly related to Antonio's question. So what do I do if I write? Well, there's a lot of people who have done lots of computations and have learned the tricks of the trade, etc. And there's available a bunch of architectures which are good. Some of them I've just put it for historical reasons. That's the Lenet of LeCun, which was where everything started. So, but I mean, the important thing is that there is convolutions, there is subsampling, which is in our case is pooling, right? In modern times, convolutions, and then at some point there's fully connected layers. Just AlexNet, so it's getting a little bit more complicated, and that was if I remember correctly, that was the first one who beat humans in this area. But you can see that the number of parameters that and the number of layers are but the objects are we just said. I mean, there's convolutions, poolings, etc., etc. That's GoogleNet. In this case, so far have been quite, let's say, linear, right? But now they start to use like more like tree structures, right? Okay, that's what is called an inception model, and that's a sort of historical architecture. The sort of interesting point is that at that point, with this ResNet with 152 layers that we just show, this is the competition of ImageNet. So by year 2015, these things were performing better than human beings, right? But this is so that's part of the sort of hype. At this time, it's probably already justified. But this is remember that this is a very narrow. This is called artificial intelligence, but this is a very narrow task. Okay. Yeah, and what is it? Sorry,
it's not clear to me what's the meaning of performing better. I mean, you show me an image of a car and I recognize the car.
but that was very easy. There's ambiguous. I mean, the images could be quite ambiguous and could be blurry. Yeah, but so I mean, basically, human experts in visualization, like you and me, we are both experts in visualization. They made error 5% of errors. So this means that we make mistakes, right, when recognizing this net it was performing better. So it's doing that task before. We saw the other day like 4 or 5 key tasks, a very basic tasks of handwritten recognition. Handwritten, it was also quite complicated. I mean, I don't know, can you read what your doctor writes?
Okay.
Yeah.
Well,
I mean, handwritten is also quite complicated.
Yeah, I cannot read what I write.
Right. So that's it. And basically, what is important in line with what I mean, a couple of questions in that direction. That's in Keras, which is openly available, and another of the, I mean, Theano, etc., Cafe, etc. They have all these. They have a few very good architectures already trained, etc., and these are quite good, right? And so there's I mean, this kind of sort of problem is partly alleviated. So basically means they have trained this with to recognize 100,000 types of objects, and these objects include, or these things include, let's say, cats and dogs, right? And therefore, if you have a problem in which you need to recognize, you need to differentiate between cats and dogs, then you can use one of these things. And even, well, we'll see it in a minute how to proceed. So final comments. Yeah, we have seen this. There's, well, we've seen this. So related with, and also with some of your things. So the first thing is this thing called in general transfer learning, right? So we can take advantage of the architectures already training in Keras, right? So we have the things that we saw before. They have already a trained. That's important. So when I was using it, it's already trained. Somebody trained. So it's a trained convolutional base and a trained classifier, and it's good for. It's pretty good. It's very good for given an input to predict, right? So what you can do is if you have a problem which is quite similar, so what you can forget about this trained classifier, but you can get this as a sort of feature extractor, and then you with your new data try to get I mean you just fit your classifier, and then it could be done quite good, right?
If I can say something, I supervised a master degree. It was last year, 2 years ago. They did exactly that. They had to classify. It was for El Idealista. They had a big databases of houses, and they had to classify that good, bad, in bad situation, medium situations, or bad. But they had very few properly classified pictures. They have a lot of pictures, but they didn't properly classified. They were trying to train it, it didn't work. And at the end, they did exactly that. They took a pre-trained standard, and then they ran it through. They fixed the features and ran only the fully connected, and it worked very good. It was exactly that.
Yeah. We are trying right now. Maybe it's connected to it, but I'm not sure. We're trying now based on tooth of monkeys, trying to forecast what type of monkey. I mean, the long term of this is to try to what type of environment was this? I mean, is it in a forest, or is it in the savannah or whatever? And basically that's what we are trying to do. Okay. So yeah, I mean, I just put here the sort of to see how simple is the code. It's we use. I mean, we could use, for example, this BGG16, and we use the weights that we have learned from the ImageNet, right? The top we eliminate, and then so it's super easy. I mean, I think I could do it, right? So therefore, you can do it. The other thing is that was one trick which is relevant. The second thing is something which is called data augmentation, and in aesthetics we use data augmentation for other stuff, right? But in this, I mean, this is one of the terms that computer scientists have reinvented. So they use data augmentation, and basically sometimes you have a few images to do this work, right? So you use this, but to do this, you don't have that many. And what you do is data augmentation, which basically gets it's based on the original data, on the original images in this case that you want to classify, right? Suppose you want to differentiate between cats or types of cats or cats versus dogs or whatever. You augment the data basically by randomly varying in terms of, I don't know, widening it or you can see the type of things that, and you can actually do this automatically as well. So there's commands to do this. This is quite good as well. And then there is another interesting thing of, we said, of CompNets. One good thing is that the first thing is that they already have, they have some, let's say, neurological connection. Another thing which is quite important, I mean, it's quite relevant, is that we can explain somehow these models. And this is a very important thing, is that in many domains, we are required to be able to explain these type of models. That's a part. There's something called explainable artificial intelligence, and basically, in general, these deep models are like black boxes, completely opaque, right? But convolutional networks can be are somehow explainable or pretty much explainable through visualization. There's various ways. I've just put a couple of examples. One is one approach is visualizing the intermediate activations. So basically, after a node processes, then after the application of the ReLU thing, which tells you what is activated, then if you visualize these activations, then you can get some explanations. For example, that would be, that's the cat, right? That's the image, and we want to explain. I mean, the model would predict that this is a cat, right? And we would like to know why, based on what. And so what you can do is try to how do you say? Yeah, try to visualize the outputs. For example, at the first level of abstraction. I mean, the first level of the first convolutional layer, right? I've just put here. I've just taken here two of the images, right? So two of the outputs, right? So you can see that the first are getting some kind of abstraction. So basically, I don't know. You could think of this is, you know, of the ears and the eyes, right? This is more focusing. This is focusing more on the I think it's called pupils of the eyes and the nose, etc., etc. At the eighth convolutional layer, if you consider the all the channels, right? You can see that it's much more abstract, but you can sometimes recognize some things. I don't know. This you could say that this is thinking of. I mean, this is maybe referring to the eyes. Etc., etc. So there's some kind of explanation that is available for this type of nodes, which is not always the case. There's other things, so for example, what is called the class activation map. There's various techniques for activation map. Basically, this is trying to find out what features or what areas, what features are more relevant in identifying a given class. And it looks something like this. And what you can do is sort of put the class activation map on the image, right? And in this particular case, it was an example on trying to differentiate between, I mean, this was saying this is an African elephant. And basically what it's saying is that the most important thing to identify this as an African elephant are the ears of the baby elephant. Okay.
No. First, it has to identify it as an elephant, and then it has to identify whether it's African elephant or not African elephant.
Yeah, this example was basically it was trying to differentiate between African elephants. I think there's something called Tusker and Asian elephants or something. There's like 3 or 4, right? So in this case, it was saying basically saying that it's very likely that there's African elephants here, and the reason or apparent reason is this part, which is the right. This is used for debugging. So I mean, if it's saying that this is if this is that if this is saying that with it's very likely that this is a picture of Modric, now that you're a fan of Modric. I mean, it would be like clearly a mistake.
Why is it not confusing the trunk for a tail? Why is it assuming that this is the front and not that is the front?
Say that again.
So the fact that it is looking for elephant is already given. It's been trained from that.
Yeah. This is like from an example. It's already trained, etc. Yeah. And it's also can be used also for object location, which comes back to well, I think it was you that of the background. So this can be used for object locate objects to locate objects. Yeah. And the final comment, which is it also puts a number of a very important problem in perspective is that a very important problem in perspective is that this can be attacked. These algorithms can be attacked, right? So that's again our MNIST. So with one of the algorithms that we mentioned, we are successful in 99% of the right. So we must say that this is a 4, right? And we are able to classify 99% correctly. We can put noise. We can put noise. So we can participate this with some type of noise. Leads to this image, and this when I see a 4 myself, I see a 4, and I do see a 4 again, right?
I see a 9.
You see a 9, right? Yeah, that's and actually the same algorithm that was working quite nicely with these let's say clean images with a 99% performance. Its performance gets downgraded to 62%. So it makes lots of mistakes with just a very, with a specific noise chosen. So this is part of, this is basically just to introduce this part of adversarial machine learning, which is a very important topic at the moment for cybersecurity, cybersecurity purposes. And there's quite a few projects going on, and in particular, we are at Ethermap. We are working on that quite a bit, and yeah, we will see. We come back, and now the interesting part is not just stock, which is an important case.
Thanks, David, for inviting me to talk. The seminar has been in Spanish all the time, and the slides are in Spanish. I'm sorry. So I'll start talking in English, but yeah, sorry, whenever you want to interrupt, just please. Is this the? Is this to?
Yes, yes.
But sorry. So I talk about the problem. What we are doing, we are predicting renewable energy production in Spain, and we do this for Red Eléctrica. That's the Spanish grid manager. And well, essentially the main goal is that production and so input and output in the system is always matches. I didn't know it had to match exactly. It matches always exactly. There's never anything extra or missing. And if there is a little extra or missing, there is a blackout. And that's like for me an apocalypse zombie. For Red Eléctrica is a blackout. It's no, that cannot happen. So what do they do? And what are the problems here? Demand.
Sorry, what happens in the other? The other is no problem, no?
Which one is no problem? Both are a problem.
If there is too much production.
If there is too much production, I think that it's not so obvious to dissipate the production. And you can, if you put too much energy into the grid, it's not obvious what to do with it.
Right.
And you can get things burning.
Okay.
And or burning or breaking. And if you have too less, you can get a blackout.
Don't you have any way to store it or something?
It's not. No.
It's not
No.
ingrained in the network, right?
No.
Okay.
Well, so these things we don't need, but they tell us when you're suddenly short of energy, what you can do very fast is open a dam,
All right. Yeah.
and that goes instantaneously off. But if you have too much, that's a problem. And they are monitoring this. So they want this not to happen. So what are the variables involved? So nuclear, gas, and hydroelectrical energy that you can adjust. You can decide how much you're going to use. Not instantly. This takes very long time to change. This you can change in. You can graduate up and down, not so slowly, and this you can do faster.
Sorry, no solar.
And these are deterministic. Say I can fix them. And the other ones, demand, aeolic energy, and photovoltaic. They are random, so they are random variables, and that's the problem. And demand is predicted, especially with time series techniques. There are some variables involved, but it's mostly time series when working that. And aeolic and photovoltaic, wind power and sun power, they depend on meteorology. And meteorology predictions, they are limit. I mean, they're not so exact. So we have two sources of uncertainty. We have the quality of the meteorological prediction, and then if the meteorological prediction would be true, to turn that into production. We don't work in the methodology part. We just take it for granted, but there is a lot of noise there. But yeah, that's the best we can do, and we try to translate that into production of wind and solar power. Most of what I will say will be for wind.
Sort of forecasting period, like one day ahead or 2 days.
I think it's written somewhere around here. The forecast you do goes from 1 hour, so from the next hour, to the next 240. 10 days. After day 5 is science fiction. Science fiction after day 5. Whatever you want, it won't matter. Because the meteorological predictions are very bad. It's not science fiction, but it's really, I mean, the error really goes up. Up to the most important range is 24 to 48 hours, because that's when the market trades. And that's when most agents decide, the ones that can decide, they decide how much they're going to produce, and that's when they sell and buy. If you are a factory and you know tomorrow is going to be expensive, you can bring down your production a little or whatever. And so that's the most important, where most agents can make choices still.
The market is continuous, or is just 1 year?
It's very complicated. There is a market at 12 for every one of the 24 hours of the next day at 12 o'clock noon. And then there are every 3 hours, there is an intraday market to adjust, make closer adjustments. And then I think it's 1 or 2 hours before the moment, Red Eléctrica takes control. Just forget about the market, and I do it because I don't want to black out. So there are markets, and the markets are, and it's important, they are designed for, so they are designed for blackout not happening. They're designed for good matching of production and demand. So they penalize you if you offer more or less than what you actually output. They penalize in both directions. So if you say you're going to put 100 megawatts, I want 100 megawatts. And if it is less, you will be penalized. If it is more, you will be penalized. So, because as I say, that's very important. And this also helps the economy of the whole thing. If I don't know how much energy is going to be put in, I need to have a gas power in standby ready to work, but that is expensive. So if you were able to predict everything exactly, electricity will be cheaper, there will be less consumption, etc.
And the penalties are symmetric now? Or...
The penalties since March last year, are symmetric. Before they were not.
What does penalizing mean?
So you get penalized economically.
Pay,
A penalty.
as in money amount.
Yeah, so far only money amount. Yeah. So what does Refresca do? They try to have their goal is that all the market agents have as much information and as good information as possible, so that people don't make mistakes and everything goes well. And for this, they make predictions, every, I think, hourly for I don't know how many hours in advance exactly they make public. They have them for 24 hours, they make public, I think not so many, but these things, I don't really, some of these details, I don't know. So how do they make these predictions? So they make these predictions from their own models, and they also buy predictions from companies providing them. The models Refresca uses so far were ARIMA, neural networks, but fully connected, mostly shallow, and support vector machines. Okay.
What's ARIMA?
Autoregressive.
Moving average. It's Bob Jenkins' methodology. It's a very traditional forecasting methodology.
So what is the data? How do you make the predictions?
What they teach in the time series course at the Complutense, that's really...
Yeah. What's the data you use? Data we use are numerical weather predictions. The numerical weather prediction is a grid of the planet with a resolution of, depends on the agency, but like the European, this is the European Center for Medium Range Weather Forecast or something like that. This agency gives the 0.1 degrees, which in our latitude is about 10 kilometers east to west and 10 kilometers north to south, more or less. That's the best agents in Europe, but also American system, and then you have like the France one, the Spanish one, the German one, and they have different resolutions. Some of them coincide, some don't. And at the end, you have like a picture. You have a grid, square grid, and for each dot, for each pixel there, you have a lot of numbers, one for each of the variables, so wind, temperature, and in different, ground level and higher levels, okay? And yeah, for the wind prediction, we use the two components of wind at 100 meters. The windmills, the axis is around 90 meters or so. Well, depends on the technology, but. And they give hourly forecast, so one for each hour. And then we also have the hourly production of whatever we are predicting. Could be a wind park, could be the whole of Spain, could be a Canary Island, could be part of Spain, whatever. We have several granulations. And there are this many hours per year. We typically use around 5 years. If we have less than 2-3 years, prediction is very bad. And after 4 or 5 years, it clearly stabilizes the quality. That begins to be enough. Before that, it's not. it's not enough. That's very rough and depends on the some of the, for example, when we predict what happens in all of Spain, the signal is very good and error is low. For a given wind park, the signal is awful. You see the error is very high. It's the best you can do, but it's very high.
Is it always with the European Center?
We so far we were using only that center, and now we are using more agencies. The best for North Atlantic is the European one. It's like a consortium of the national agencies.
But it's better than the Spanish one?
It is better than the Spanish one. Yeah.
The spatial resolution that you have is 10 kilometers by 10 kilometers.
Yeah.
Right? So if you have a wind park, for example, the extension of the wind park, the surface that it covers, is just encompassed in one single patch, I guess, no?
Yeah, depends what could be. Yeah.
Most likely,
Yeah,
right?
yeah,
Maybe two.
Yeah.
So have you, I mean, do you have enough spatial resolution to make like a precise forecast in there? So you have like one single dot for the whole park in most cases, I guess.
I would love more spatial resolution, like the window of my,
Right.
but that's actually not the problem. The problem is that the whole resolution is crap. When the agency tells you the wind is going to be this much, that is the average of the wind speed for the 10 minutes before, say at 12 o'clock, they give you the average of the wind speed between 11:50 and 12 o'clock.
Okay.
And you need to use that to calculate the energy produced between 11 and 12. So spatial resolution could help a little. And also it has, well, I mean, it's very difficult to predict when, so you have wind and there is wind coming, but it's very difficult to predict exactly. So
yeah. And among the models they use, do they not use something like fluid physics or something like this?
that's what they use, the agencies. Yeah, it's physical, how do you call this?
Engines or
¿Cómo se llama? No sé qué fluidos, ¿no? Dinámica de fluidos. Pero that's the equations behind. That's a supercomputer solving them, and that's the output. What we get is the output of those equations. Yeah, some companies that do this, what they do, they are methodologists, and what they do is that, okay, if you have an orography of and you have a prediction, maybe you can fine tune the methodology. We don't do that.
Okay.
These windmills, do they change direction?
Yeah, of course. Yeah.
How?
Like 360 degrees.
I think most technologies, yes, but I'm not totally sure. But you usually set them in a place with prevailing winds. But I think they do turn 360, but I'm not sure. Okay. That's the data for wind. For photovoltaic, for solar, you can use the radiation and clear sky radiation without clouds. Temperature, because it affects physically. Wind, because it dissipates temperature. And then, of course, the incidence angles, okay? For solar energy, we have much less data because they are more new. We have longer series of wind power. At night, there is no light, so you have half of the data. And there is something also relevant. At midday, sun is much more intense than in the afternoon or in the evening. So when you try to minimize error, somehow the neural networks only look at the midday. We're trying to learn how to use the other hours. It's not so. We've failed with several approaches already. In turn, then in our help, it comes and it seems that solar scenarios are much less diverse, so they're more predictable. So when this started like 3 years ago, that when Red Eléctrica made an open proposition of research and how do you say this? Research and development offer that you could, they wanted to apply So it was in, I think, 2015, right? Like you said that it was the CNNs that become to be very trendy. Already in 2017, there were several proposals in the literature saying, okay, let's use this for exactly this. And in 2019, Red Eléctrica are very good predicting energy in the world. One of the very good people. And so they decided to open this research line to see if this could be used. And we presented a proposal that was essentially based on what you have said and based on the literature existing. There was nothing super fantastic, super new. And the proposal, yeah, is exactly what I said. It's a numerical weather prediction is just a picture formally. So let's use that kind of tools. The architectures, we've tried many different architectures. As you were asking before, how do you decide architecture? So by trial and error. Trial and error has been very much done for image recognition and has been very little done for this. So we've been 3 years now trying and making errors and trying to fine tune and choosing the parameters and choosing the number of filters, the size of filters, the number of layers, blah, blah, blah. The thing is that because there's so much noise in the data, what we have seen is that there are many architectures quite different that perform comparable because the problem comes from behind, from the data quality. So the one we are using mostly is something like 3 convolution layers with pooling afterwards, and then will be one fully connected. This is not a classification, so this is a regression. So okay, we have, I mean, after fully connected, 1 neuron.
A question. So the convolutions you're using are 2D convolutions over.
Well, we have several architectures. I think I will say something. I will say something just a little bit in the next slide. Yeah. For wind, that is what they call the persistence of wind. So you have the data, the prediction. The prediction is something that could happen. Okay, you can take it as that. And when you are close to so if I'm in now and I want to predict for the next hour, I have another information that was the production right now. This I have. So this updates the data that comes and that you receive. And so that's very useful for the first 6 or 7 hours ahead. After that, there is no persistence. The information is not useful anymore. So for the first horizons, we do the 7, 6, 7 hour. It's useful if you have it to use the last available production of your part or Spain or whatever. And how do you put it in? You put several productions in the fully connected directly. You can do one LSTM just with the productions or several other possibilities. They perform comparably.
Wind speed, what is the minimum wind speed that is absolutely necessary, and does higher speed make production faster?
I don't know when they stop. I guess I could see it. That depends on the technology of the windmill. So it's not the same for every windmill. When there is very little wind, they totally stop. When speed is too high, I don't know how they do it. They don't produce energy. But I think you stop it. You let them run loose or something.
In between.
What's the range?
Yeah,
so from essentially 0, depending on the technology, and I think they stop at something like 90 kilometers per hour. Again, depends on the technology.
Between that, it's a linear thing.
It's not linear actually. It is sort of, well, it goes almost linear with the square of the that's energy. It will go almost linearly with the square of the modulus of the speaker. Just for instance, we've tried ResNet before, just to give a chance, and it's much cheaper. It took much longer to train, and it was totally comparable. Maybe a little worse on the complex architecture.
Are you using Lovelace or
we are doing this? I'll go on that. At the beginning, we were doing everything on Lovelace. Now we are kind of going industrial, and we had to jump to a Amazon Web Services. And as I said, our main problem is the error in the input. We don't know, we never know, not even for the past. I don't know what the actual wins were at any moment. What I take as a proxy for the actual wins was the best prediction I had. But that was not a real win. That's just what I got. Yeah? We have to train always to minimize how should I say in English?
Absolutely.
Mean absolute error. That's a standard in everything. And we have hundreds of thousands of parameters. This regularization is crucial. Otherwise, specific problems we deal in this, and again here I'm somehow talking in the that again related to your question before. There's a lot of heuristics, trial and error done on image recognition, and here we have to do this from scratch essentially. So the each data is not separate, but it's on a time, it's a line on time. It's, in a way, it's a time series. It's clearly a time series when you're doing prediction in the short range. It's not so clear when you're doing for a longer range, but in a way, it is a time series. So we can use video tricks, and then we can use 2D convolution, just we fix the hour and we convolute on this map. And we could consider a span of hours around it and convolute or do something different. I can do LSTM, so convolutional LSTM. I can do a convolution plugin with an LSTM structure. And there are several tools that have been used for video treatment. And again, when you do it, you have this slow function they call, or from the beginning convoluting in time, or you can start convoluting only like in a space and at the end in time, and the layer, and with a lot of trial and error, mostly a lot of error.
Have you tried space-time models, like dynamic linear models in space-time, etc.? That kind of.
No, would like to hear.
That might be
okay. Then we can make it. Yeah, would love to hear. So we have that when I got persistence in the first hours when the information of the last production is still relevant. Then we use LSTMs or just, as I said, just plug the production to the fully connected. And then things which are probably for statisticians very basic for us. At the beginning, we have to be very careful. We made very stupid mistakes. Of course, if you typically split train value tests randomly, that's totally crap, because if I use 7 o'clock and 9 o'clock for training, I memorize 8 o'clock. It's very stupid, but we have to run into that kind of thing. So now we take blocks at least 100 hours so that they don't contaminate from the. Often we don't have so much time available, and then sometimes it's a problem. We cannot do data augmentation. We cannot rotate the wind because it will be different. There's no rotation invariant, no rotational invariant. And we cannot do things like, okay, make a small perturbation, like Gaussian perturbation, because it's not classification, it's regression. So a small perturbation will turn into some perturbation of the level that I cannot. We've tried several data augmentation techniques, and everything we have tried has failed. And there's uncertainty in inputs, and we don't know real wins. And then there are several tools that are methodology they use. They call ensembles and Pullman's ensembles. We're trying to learn to use those now. Well, Pullman's ensembles we've been using already. Ensembles we're using now. When you make the numerical weather prediction, what the agency does is solves the model, and you get a prediction they call the deterministic model. And then what they do is you solve the model for a given initial conditions. And what they do is that randomly perturb the initial conditions, and then solve the model for the randomized from the perturbations. And then you get, they do 50, they call it ensembles, it's an ensemble of the scenarios. And they have less spatial resolution, but they should be useful. The cheap way, and they're called in the literature Pullman's ensembles, the cheap way to do this is you get a run of the, because it's a supercomputer solving these problems. And you get a run of the computer at for the European Center is at 12, at 6, so at 00, at 6, at 12, at 18, at 00. So if you use for your prediction and each of these runs tells you the prediction for many hours in advance. So for the hour now, I have the last available prediction, the previous to last available prediction, the previous to last available prediction, blah, blah, blah. And up to like 10 or so. Oh, well, actually more. Not much more. And so those are, in a way, they are like different scenarios of what could happen today. And they are useful to train. If we use them for training, we get better training than if we just use the last prediction. And ensembles, so far, we were able to use, but not so much. And then these things are big. We feed a lot of data into the memory, and we've had problems saturating RAM. And then we have to learn tools, carefully use batches to put this in. And we have to use this tool. I don't know if any of you have to use it. It's TF Records, it's TensorFlow Records. It's the tool, a tool they developed to deal with large amount of data to fit them. It's very complicated to use. The documentation is very bad so far. It was in beta until recently, but now we can use it. So if any of you ever has a problem with feeding data into RAM, now we can help really. And this is just like where we are more or less. This will be these 3 lines here. We are blue. We are blue, I think. Yeah. Yeah, we are blue indeed. Orange is the combination of the predictions Red Electrica had, their own and the ones they buy, and they combine them. So we are totally comparable to that. And gray is just the semi-sum. So our prediction plus the one of Red Electrica and divided by 2. This is for 2022. So we are totally competitive here.
How come the gray one is below the others?
Yeah, because there is a little bit of cancellation of errors. Our errors happen we all have to deal with a methodological error, and then that is common to everybody. And then there's a little cancellation of errors in the models. Yeah. Just to give you a range of the magnitudes, this is for all of Spain. Error, so will be around, say, you cannot see it here because of this, but it's like 24 hours more or less around here. In 24 hours, the error is around 2% of the installed energy, but the average production is 22%. So where the error is around 10% of the production for all of Spain. For a park, the typical error in 24 hours is 9% over an average production of 22. But that's what we can do. We have no park that we have trained with an error smaller than 6, and some have an error of 15 over an average production of 22. Okay, so but that's what you want.
I have one question with the graph.
Yeah.
Why do you have these smaller errors in the?
Yeah. Sorry, because can I skip? Can I
don't know.
remove the black thing just for a moment on this?
We can try it. Later on.
That will be good. Now you can leave it there. What you have here, so this is how many hours in advance we are making the prediction. This is 1 hour in advance, 2, 3, blah blah blah. So for the first hours, you get the last production is super informative, and you had a very small error. And as you can see, the degrades up to the hour 7 or so. Degrades very fast. The information up to here, you have that the meteorological prediction is less and less significant as time goes by. But this fast growth here is because up to here you can profit from previous information. And after that horizon, you cannot anymore. Okay, so now we are in an industrial part. So far, within 3 years with this. At the beginning, it was proof of concept. See if this can be done, and yes, can be done. And now we are like kind of becoming like a company in a way, and we're trying to actually become a company. And the model has been tested for more than a year, and now they're using it. They're putting in production is they're beginning to use it. We've already done a predictor for each of the wind parks in Spain. Like 1,200 of them, and that was a lot of computational time. That was because for each park we make several networks, blah blah blah, and so this was.
They're very different. I mean, this 1,200, they're very different. They're
Yeah, for each park you have to make it. We do some transfer learning. I talk about it next, but as I say, you have to train for each park. And for each park, because you have that in the first hour you do something, in the second something. For the first hours, you have to make a model for each of those hours, and then after hour 8 or 9 or so, you can make the same model for all of them. But then you have several models for each park. So this was around 6,000 GPU hours. So we had to go to the famous cloud to do some of these things. We've also used Lovelace a lot. And now we are trying to become a company, to sell this service to whom? To wind park managers. You need a good prediction to go to the market because they penalize you if you don't have. So we do transfer learning. How do we train for parks? Like parks we have from Red Eléctrica data like from Murcia region. Okay. So we train like the Murcia region, and we take those features, and then we don't fix them. But what we do is we initialize, not randomly, but we initialize the training of the park, which is in Murcia region, with those features. This pre-initialization, not random, that does not improve the quality of the predictor, but does makes the training much faster. It takes like more or less half of the time. So we'll have in like 10,000 hours otherwise. Okay. I would like to say something about what we're doing with these ensembles, because now for us now that is becoming like significant, and would be, I don't know, probably you can help us here. Well, the download times are unbelievable. We've been downloading for 6 months. There are 50 ensembles, and in 6 months we got 5 of them for 7 years and 50 of them for just 1 year. So it would take years, literally, to download all the ensembles that we want. That's for Spain. This is just training with a deterministic model, and this is training with ensembles also. So you get some reduction in the same region and the same test set. You get some reduction in mistake, in the error. And this one, next slide is more a question that we wanted to use ensembles for. They're asking now to give us intervals, confidence interval. So I want to be 90% sure that the function will be between here and here. That's very relevant information. Our naive thing would be, okay, we take the ensembles, we just predict with each ensemble and look at what happens there. That would be the naive approach. Wrong. Wrong because of this. I try to explain this graph. The solid line here, that's the actual prediction, that's the actual production. The also solid but purple line here, I don't know if you can see it well there. That is our prediction using the deterministic model. The band there is a density band of the predictions of the ensembles. This is in 16-hour horizon. Consistently, real prediction and our prediction is like percentile 80 or so of the ensembles. Why? I don't know. I expected it to be percentile 50 in the median. Totally wrong. Okay, well, that's all we. When you get to longer time, that's something that will be like 80 hours or so in time, 80 hours ahead. Then this does happen. So the actual production is somehow at least in the convex curve of the, and it goes not to the median, it goes to percentile 56 or so. No idea why this happened, but this I wanted to discuss with you one day, so I can show the picture. Want to discuss, I want to ask you for help for my second.
We have Solari now.
Okay, so in photovoltaic, in solar, we have worked less so far. There is less data. We're still fixing the architectures from fully connected neural networks to convolution to LSTM and some other things we still want to try. We still don't even know which are the relevant variables. We know which appear in the literature, but some of them you plug them in and it doesn't help. So we are still trying. Again, it's trial and error procedure. This is where we are more or less, and the green line is us. And this is the error we have. That is not in different horizons, that is in different weeks, I think, of a year. And red and blue lines are the predictors of red electrica, but the predictors of red electrica for solar, they are very bad, and they know it. For wind, they're good, but for solar, they know they're very bad. Solar was not an issue until 3 years ago. It's become an issue now for them. And yeah, well, and just here, this would be like from one big some part, just some data of the errors, because they're very different. Naive we call just solar is very predictable. So just for today at 12, prediction will be what was to yesterday at 12. That's not so bad. It gives you an error of 7. We made a good linear regressor, probably much worse than what you would do here, but not so bad. That was an error of this much. With neural networks, so far we were somewhere around there. Error is much less. This is for the hours of light. And in the hours of light, the average production is 40% of the installed power, and this is over installed power. So the error is somewhere for a solar park is around 10% of the actual production. In the wind, it was much worse.
Sorry, why did you say solar production of today is predictable by yesterday's?
I mean, that's the most naive. We use that as a benchmark because solar production
conditions remain the same.
Yeah, but like
today it's raining in Pretoria. I can see my solar production.
No. But you put solar plants in Spain, mostly than in Murcia, where it rains 5 days a year if you're lucky. So if you see the time series is.
So your lat long matters.
Yeah, and then we use just as a benchmark, just to know what would be the most what I call naive. Okay. But well, error is much less. Also, the variability of conditions is much less. So it's more likely we can do transfer learning from one solar power plant to another, but this we didn't do yet. Yeah, that's what I got. So thanks.
And you said like 3 years ago, this was not an issue.
Solar was not an issue yet because
now it's important because of the boom, or
because so now when we started with this 3 years ago, I think there were 21 gigawatts of installed wind power. Now there are 29. And I think in that time there were 6 gigawatts or so of solar. I think now there are 15 gigawatts of solar, and it's been installed faster than wind. So in the world now, there is more solar than wind. That changed recently, I think. And in Spain, it's going to change in a few years.
But this is because everybody's putting.
No, well, also, I mean, there's a lot of so individual, but also price of the panels became much cheaper a few years ago. And before that, it was more expensive to buy the panel than the whole output. and now that has changed. So now they are efficient. They don't have any government help anymore, and they are sustainable. So, and it's I mean, they expect to have, I don't know, I saw the expectations of installed power, they were huge. And it's going to become, for Refletica, it's going to become more and more of a problem. Because although it's very predictable, you have things like in this Mula, when suddenly there comes a cloud, as there was the cloud coming, and then of course the production goes, and when the cloud leaves, it goes boom. And this is the kind of things they don't like, so they have to deal with those things. There is something they call nowcasting, I think it's called. It's for the next 10 minutes. And you do this, put in cameras like this, and it's in the clouds, and nowcasting for the next 10 minutes. They don't do it, Refletica don't do it yet.
I would assume that for those windmills, the objective would be to produce as much as possible. I mean, why do they need to know the prediction?
To sell it. You have two problems for selling the windmill. First, you have to decide which will be a good place. That we don't do, but there are a lot of companies specialize in that, in choosing the good places. There is a map of resources, it's called by the Spanish government, and so. And then once you put it there, you cannot move it around. It's there. It is fixed. Now you have to sell your energy to the market every day, and you're going to be penalized if you sell more or less of what you sell. So you want to know.
Okay. You have these predictions for the whole plant, for example, right? Mm-hmm. If you have a plant of solar panels, mm-hmm. you make a prediction for the whole plant. Mm-hmm. You could have some type of information without the need of cameras or something like that. If you had information panel-wise, if you
for solar power, I think not. For wind parks, some of them have the disaggregated information for each windmill. Yeah. So maybe a park will be 20 windmills or whatever, 50. So some of them have disaggregated information. And then you can try to make a model for each. Yeah. The problem when you do those things, what we have seen, is when you disaggregate too much, the signal is too noisy. Mm-hmm. So of course, it seems that you would get a profit, but this does not always happen because signal is just too noisy. Okay. It's too random. I mean, this is dynamic fluid. Fluid dynamic. To me, I imagine it like seeing I mean, you're in like a river running fast, and you try to predict the shapes. Yeah. General shape, particular shape is chaos, and this is they have chaos phenomena in those equations. So signal becomes too chaotic, and.
But with the example of the cloud, you could do something, I guess.
With the cloud, yes, the cloud seems to be much less chaotic.
Yeah.
And that's why they are doing nowcasting, and that seems to work. Okay. For instance, they have a problem with wind parks in Canary Islands because they have this thing they call ramps. There is suddenly the wind goes up by a lot. In Canary Islands, they have a lot of windmills. So out of the blue, you get a sudden ramp, and a sudden ramp in production, and they have problems. They're not so easy to deal with. And so you have things, and that makes the signals very chaotic. The output coming from each generator is too random. When you sum them up, it becomes more stable. Sure. We have some parks when we train, and the network does not train. It gives you the average. It says always outputs production 22 because it was not able to do. We have to tear down parameters and do things. If it is very small, it's too chaotic. Yeah.
So going back to the windmills, if you are penalized if you sell too much, would it be advantageous to switch the thing off?
But it's probably not so obvious how to switch them off.
Okay.
That is they are holding the wind. I don't know how they do it, and I think by law they can't.
Okay.
But they do it. We've seen it. When the price of the energy is too cheap,
yeah,
the actually produced energy is much less than predicted, and that they cannot do it, but they do. Because if they're going to sell too cheap, just the friction of the windmill and so is not worth it, and some of them are turned off. And that's going to happen more and more as